Welcome everyone, and today's webinar is given by Professor Matthew Gilbert from the University of Sheffield, and it's on application of layout optimization in engineering analysis and design. And I'll hand over to you, Matthew.
Okay, so as we mentioned, I'm going to talk about layout optimization and how we can apply that technique both in the analysis context and also in the design context. So just give you a quick rundown of what I'm going to cover. I'll start with a bit of background and then dive into design applications of layout optimization. And you can see on screen there an example of use of truss layout optimization to identify a potential design for a structure, sort of portal structure. I'll then move on to analysis and how we can apply something called discontinuity layout optimization to evaluate the safety of various different types of engineering structure or construction. So on screen you can see evaluating the safety of a geotechnical foundation on the left and establishing the safety of actually a reinforced concrete slab on the right there. And then I'll wrap up with some conclusions. So before we get into the webinar proper, I'll just say a few words about ICAIR, the Integrated Civil and Infrastructure Research Centre. It's a new University of Research Centre. I've just picked out in bold a couple of the points from the vision and mission statement of the centre that are relevant to this particular presentation today. So resource efficiency, physical infrastructure is one major issue that we're focusing on. Clearly, we're in the light of the climate emergency. It's a very important topic, and it's an area that we're very interested in, and we'll be effectively covering in more detail in this talk. And secondly, one of our aims is to pioneer the introduction of technologies capable of delivering step changes in the design of construction infrastructure. And so that's also going to be something that we pick up in the talk today. And actually on the screen you can see a view of an optimized timber truss in the ICAIR laboratory, and that particular truss has actually been designed using some of the truss layout optimization techniques that I'll be talking about in the webinar today. Okay, so first of all, I'll just have a bit of context to proceedings. As an industry, as a construction industry, we currently spend about 60% of our effort on new construction in the UK and 40% on existing infrastructure. It's a big sector in the UK, about 110 billion pounds per annum, and perhaps even more importantly, it's a major contributor of CO2 emissions. So something that's really significant given the current climate crisis that we currently face at the moment. I think that breakdown between existing and new infrastructure has got to change for that reason. So I think we're going to spend more and more effort on existing infrastructure, so retrofit, rehabilitation and so forth, and less on new construction. But of the new construction, it's really important that we focus on reducing the emissions associated with new construction. Construction industry's been plagued with low productivity for many years. Or certainly the increases in productivity have been much lower than in other industrial sectors, and there's some particular reasons for that. I mean, one observation is that we're very often dealing with one-off constructions. So unlike a product in, for example, the mechanical engineering sector, we're not able to refine a design and then produce thousands or millions of those. So we have only a limited window of opportunity to refine our designs. And the other thing is that we're often dealing with quite difficult materials in terms of their mechanical properties. And I'm thinking of things like soil and masonry, which are much less well behaved than you know, many materials used in for example, normal manufacturing sector. So just to sum up, we've got limited time to get refined solutions, but what we really need is rapid and effective means of getting close. And what I would argue is that the tools that we currently have at our disposal to do that are pretty blunt, frankly. So on the analysis side, we've got hand calculations or automated hand calculations on the one hand, and then on the other hand, we've got complex, slow-running, nonlinear numerical analysis methods. And we don't have tools that sit between those two extremes. And one of the areas that I'll be talking about in this webinar are the sorts of techniques which sit between those two, and hopefully provide engineers with scope to come up with better models, analysis models, or in the design context, better designs. And what I would argue on the design side is that the process of design in civil engineering has been largely unchanged since the 19th century, in the sense of we come up with a manually conceived design, we analyze that design, and then depending on how much time and resources we've got available, we may redesign that once, twice, 3 times, however many times that we can, but probably not very many times. So we do that in an ad hoc, fairly manual manner. And I'll give you an example of an analysis problem where problems arose. It's an example that I've especially chosen for this talk because it relates to Liverpool, and this is a Liverpool University webinar. However, it's a few years old now. So many of you will be aware, if you've been living in Liverpool for some years, or if you're not from that area, you probably won't know. But in the mid-2000s, there were plans to replace Liverpool Football Club Stadium with a brand new one, and that design was quite well advanced. And actually, in 2008, they actually went on site and started to do groundworks for the new stadium. And the only thing that stopped it was the financial crisis of 2008, which led to the whole project being abandoned. But in terms of the stadium, it's quite an interesting design. It actually had the whole of the roof structure supported by 4 inclined columns, and those inclined columns impart large forces on the soil underneath. And from recollection, I think the forces were of the order of 34 meganewtons at each of the 4 corners of the stadium, and those were to be inclined an angle of again from memory 39 degrees to the horizontal. So far so good. But when the groundwork started in 2008, started digging into the ground and found unforeseen conditions, and the contractor of the time, Laing O'Rourke, got back to the consultant who'd done the design and said, we were planning to put these in at 39 degrees, but we're no longer able to do so because we've found X, Y, or Z in the ground. Would it be okay if we change the angle from 39 degrees to 45 degrees or whatever? The consultant at the time had spent months and months and months refining the design using complex nonlinear finite element methods and also some very complex hand calculations, and weren't able to give an instant reply. And days, and if I remember correctly, probably weeks went by and no answer, no new design was provided. And all the while, expensive plant is on site racking up higher charges. So what happened was that the contractor, Lang O'Rourke, were the very first customer for the Limit State Geo software. Limit State is a spin-out company from University of Sheffield. And they bought the software, and in a matter of 2 hours, they were able to do a full parametric study looking at the influence of the factor of safety on the angle of the foundation to the horizontal. And they were able to quickly establish that that by changing the angle, increasing the angle, the foundation would still be safe. So this is an example of a sort of a mid-range analysis tool, in this case using the discontinuity layout optimization technology, which I'll talk about later, to give good solutions in a very short time frame. On the design side of things, automated tools with the ability to explore a wide search range space are not readily available in the civil and structural engineering application area. On the other hand, in some other areas, for example, aerospace, automotive, for example, continuum topology optimization tools are available. So the idea with such a tool is that you specify the design space, you specify where potential supports might be, what the loading is, and then you actually chip away at the original design space to reveal a residual structure like the one shown on the right. So in the case on the right of this image, continuum topology optimization has been applied to a building design problem with interesting results, I would say. Now, the main problem applying that kind of technique to civil and structural engineering problems is that you have to specify a volume fraction. You have to specify what proportion of the original design domain is going to be occupied by structure. And it only works really well if that proportion is quite large. So if 10, 20, 30% of the original design space is occupied by structure, it works pretty well. If it's very small, as it is very often in civil and structural engineering problems, typically it's a small fraction of 1%, then the approach works much less well. So one of the areas we've been focusing on for the last few years, and I'll talk about today, is something called layout optimization, where instead of adopting a continuum representation, we actually deal with discrete structural elements, for example, truss elements, to identify an optimal truss structure, for example. So moving on to the design side, there's a big opportunity to apply optimization in general, I think. So, for example, changing the shape or size of structural members. And Arup reported a year or two ago saving 700 tons of steel by doing size optimization on the scalpel structure in the City of London. But what I will argue is that changing the layout of members has the potential to reap significantly bigger savings. So the layout is, how these members fit together, how they're aligned, and so forth. So what does an efficient layout look like? Well, I'm going to start where most people start in this space, with a truss, and go back to some seminal work done in this area by an Australian engineer called Michell back in the early parts of the 20th century. He showed that orthogonal layouts of elements give rise to mathematically minimum volume structures. And in the example shown on screen, actually we've got a central point load going downwards, vertically downwards at C, and then we've got supports at A and B. And you can see that the optimal structure comprises a series of orthogonal tension and compression elements. So these are, at the bottom, we've got a tensile rib, at the top we've got a compression rib, and then alternating tension and compression spokes. Simpler structure is quite useful in showing what the importance of respecting that orthogonality is. On the left-hand side, we've got a pair of members, a tension member and a compression member, carrying a force some distance away from a rigid wall. And if we compare the volume of the structure on the left with the structure shown to the right, we can see that we save significant amounts of material. So the structure on the right, for example, is more than double, or requires more than double the volume of material than the structure on the left. And that's got an angle between, a subtended angle, I think, of 22.5 degrees, then 45 degrees, then 90 degrees. Now, you may say, well, I know that structural engineers don't use these shallow angles. Well, I beg to differ. You see examples of shallow angles all around you. Sometimes there may be important considerations which mean that it has to be a shallow angle, but in other cases that's not so clear. And here's just an example that you can see around you. It's part of a pylon carrying electricity. I am not particularly familiar with the particular design constraints and whether it would have been possible to have a larger angle there or not. A slightly more complex example shown on the next slide, where we've got again a spanning structure. We've got supports at the ends of the structure, and then we've got a series of point loads in the span. And the top structure is a classical Pratt truss, and the bottom structure is an optimized truss. And what we see is a significantly lower volume by using the optimized structure. And again, we have orthogonal or near orthogonal tension and compression elements, which give rise to far more efficient structures. Now, I will say the orthogonality applies when you've got a dominant load case, single dominant load case. It's not quite that simple when you have multiple load cases, unfortunately, but there's still scope to have big savings when you use optimization. A case where you typically do have a dominant load case, certainly when the span is very, very large, is when you have a long span bridge structure. So here we've got 3 for the price of 1, so to speak. We're up in Scotland, spanning the Firth of Forth. We've got the Forth rail bridge on the right-hand side, and then 2 structures particularly interested in here are the original road bridge, suspension bridge, shown in the middle, and then the new Queensferry crossing shown on the left. And what you can see again is a case where tension and compression members are not orthogonal in either of those structures. And what does that mean? It means that more efficient structures exist. And here's an example of a structure where the tension and compression members are closer to being at 90 degrees, and you end up with significant benefits in terms of reductions in volume, or in a long span bridge structure, the ability to span further for the same with the same material. So this particular image is actually from a paper we published a couple of years ago, and in this particular case, the design shown requires less than half the amount of material as required for the ICAIR suspension bridge in Japan, which is currently the world's longest spanning bridge structure, or longest single span at least. So the big challenge is is benefiting from the theory. We've known about optimal structures for more than a century. How can we bridge the divide between the mathematically optimal forms that we see, for example, on the left, and a practically realizable structure, making use of fabrication methods, which might be traditional, or they might be some of the emerging digital fabrication methods. So, for example, laser cutting, 3D printing, and so forth. So that's the challenge. The way we have been approaching this is entirely numerical. So whereas Michell's work was analytical and theoretical, we've been building on some work that was done 60 years later than that by some American mathematicians who basically formulated a numerical trustless optimization method, which is well described by the 4 images you can see on screen now. So the idea is that you have an unknown design space, load, support configuration. You populate the design space with nodes. You then interconnect those nodes with potential truss bars, and then use optimization to find the minimum volume subset of members that then form the optimal structure. In terms of mathematics, it's nice and simple. What we're doing is we're minimizing the volume of material, which is simply the sum of the lengths times the areas of all those bars that you saw in that so-called gram structure in the previous slide. We're enforcing equilibrium. So equilibrium between the internal bar forces and the nodal forces. So equilibrium in the x direction and y direction at each and every node. We then impose limiting stress constraints, and finally we enforce the area variable having only a non-negative value. It doesn't make sense to have a negative area. So in optimization problems, we're minimizing the volume subject to the constraints shown with internal bar forces and cross-sectional areas as the problem variables. We can also include a number of different load cases in our formulation without too much difficulty. So slight change. Now, instead of having a single system of internal and external forces, we have a series of them, and basically we're simply checking that the stress constraint is complied with for each and every load case, and clearly the area of each member has got to be sufficiently large to carry the worst case load case. Okay, so actually move on to an example. Here we've got some forces to be carried. We've got a couple of supports, and we are doing a layout optimization using the same method as proposed by those American mathematicians back in the 1960s, with one exception. Whereas they suggested that you connect each node to every other node from the outset, here we are initially only connecting adjacent nodes, and then we are using an adaptive member adding scheme to only add additional members to our ground structure where needed, and we end up guaranteed to converge to the same solution as we would have done using a fully connected ground structure, but with far less computational effort and with far lower memory requirements. However, the structure itself leaves a little bit to be desired. This is a truss, it's a pin jointed truss, so you can see that the uppermost member in compression is actually in unstable equilibrium. If you were to knock it with a feather, it would fall over. You can see quite complex arrangement of tension and compression elements, which if you were making those, whatever the processing, even 3D printing, would be potentially quite troublesome. And also we might have we've got some thin elements in compression, which may be prone to buckling. So we've got a few areas to focus on, and these areas have really, in my view, prevented the 1960s numerical method from ever taking off in practice. So industry hasn't been using this technique because of these shortcomings. And so what we've done in the last few years at Sheffield and also at partner institutions in Edinburgh and Bath is we've been trying to address this in a systematic way. So a number of steps shown on the current slide. We rationalize the solution via geometry optimization is the first step. Geometry optimization involves modifying that optimization formulation so the XY positions of nodes or joints are included. So we solve the layout optimization problem, then we solve another problem that also involves moving the nodes, and that has two benefits. One is that you end up with a lower volume, but two, potentially more importantly, you end up rationalizing the solution. You have nodes merging, and the number of members naturally reduces in that process. If we want to simplify the solution further, we can do, and various ways we've explored for doing that. Similarly, we can change the formulation from a standard linear optimization formulation that you saw in the previous slide to also deal with either local or global buckling instability, so a more complex formulation to deal with those. And then finally, I've been focusing on trusses, but for example, in a typical building, when you look at the floors, generally we don't see very many trusses. We see arrangements of beams, so potentially we can use beam grillage layout optimization to identify efficient arrangements of those members. So first of all, just think about rationalization. That's the first of those four steps. Here we've got shown on screen the solution that we get from the basic layout optimization solution process, should I say, where the nodes are in a fixed Cartesian grid. Looks quite messy. If we start to do geometry optimization, then you can see the nodes moving around, and very, very quickly you can also see the solution becoming much clearer. This is actually the Michell sphere problem, which is the only 3D problem that Michell showed in his 1904 paper. Next up, simplification. So various different ways of doing that. One that we found very helpful is to have a two-phase process where we first of all solve the layout optimization solution, also apply geometry optimization as well, and then fix the volume and so change the volume from being an objective to being a constraint. And you say, okay, if I am happy to accept, for say, a 4% or 5% increase in my volume, show me the solution when I'm minimizing the number of members or minimizing the number of joints. And what you can see is that by varying that percentage, a trade-off, percentage increase in volume, you can see a whole family of different structures, and you can choose what trade-off is appropriate for your particular application. And this particular formulation involves having a smooth representation of on-off binary variables. But You can also do that more rigorously using mixed linear programming, and we had a paper out some months ago doing just that. Another thing I mentioned was buckling stability, either global stability or local stability. Here we can see an example where we're addressing the global buckling stability problem. In this case, rather than solving a linear optimization problem as we've done in some of the earlier examples, we move to a semi-definite programming problem. It's more complex, more computationally expensive, but the benefit is that rather than coming up with solutions which are prone to be globally unstable, you end up effectively having something that is automatically stabilized. An example you can see on screen now, perhaps not super clear, but we've got design for a grandstand roof, and at the top we've got a series of planar trusses with no connections between them. Now, there's a danger that those could become globally unstable, or they could buckle. If we introduce the new stability constraints, then we end up with a series of diagonal members between those planar trusses, and we end up with a much more robust structure. And the way we've solved it is using also the member adding technique that I mentioned in an earlier slide with good effect. So we're able to get an order of 5 or 6 times speed up, and also reduction in the number of bars and hence in the memory footprint. Final thing I mentioned, I think, was grillage optimization. So fortunately, we can apply exactly the same approach as we apply to trusses to beam grillages. So this is arrangements of beams to carry specified loading. Assumption is that the beam has a predefined depth, and we're now looking at effectively the width of the beam. And we published details of this a couple of years ago in structural and multidisciplinary optimization. The interesting thing is how much more efficient these idealized, optimized beam grillages are to conventional designs. So if we're looking at a plan view of a floor plate of a small building, on the right hand side we've got 4 columns, and then we've got orthogonal secondary and primary beams, whereas on the left hand side we've got the optimized design for the same problem. And most of the load in the left hand side actually goes through columns at the centers of each side, but there are also smaller columns all the way around the perimeter. But the key thing is that we now have a different layout. We've got beams that are spanning at 45 degrees. And the other thing we're doing here is we're allowing the width of the beam to vary along the length of each of them. But the difference between the amount of volume of material that's consumed between the benchmark and the right hand side, the more conventional, is quite astounding. It's more than 5 times as much material required for the conventional floor plate that we've typically designed. Now, the example shown on the left is unlikely to be realizable in practice. However, one would think that there's definitely an opportunity to find somewhere in between where you have a significant saving in the amount of material compared with the conventional design. And these techniques, as part of a recent research project, have been embedded in a plugin for the parametric modeling software called Rhino with the Grasshopper plugin. And what we've done is make that available, so you can download that software from the hyperlink shown, and we've actually made that available to people in industry as well, and they're finding it's giving them some really interesting solutions. If you're not familiar with Rhino, Grasshopper and parametric modeling, this is also similar to using Dynamo in Revit. Basically, what you can do is control the geometry using a series of sliders. So instead of fixing the geometry, you can vary the geometry parametrically. So in terms of Peregrine, what we're able to need to do is specify design, domain, and the loads and supports. We then have a solver component, and then we can parametrically vary the geometry. So for example, the positions of the loads in this case, to see how that influences the solution. So this is real time, so you can see it's only a small problem obviously, but you can see how you can very quickly and easily see these how these optimal forms vary depending on where the various loads and supports are. So that's an academic example. If I move to a slightly more practical example, this is I'll just fast forward. So this is using now the plugin to optimize both the truss elements, that's the bracing elements, and the sort of the vertical load carrying elements, but also the flooring as well, using the Grillage optimization. So we end up with just pause it on the, you can see the Grillage. Yeah, so you can see the these 45-degree angles again that we saw in the previous example. So potentially this can do two things. One is it can give a benchmark to the practitioner, so they can compare this design with the design that they were planning to build anyway. But more importantly, it can act as a sort of driver for change. At them, if you find that your design has 4 or 5 times as much steel as the benchmark, then what can you do to move your design closer to the benchmark? And then finally, on this area of design, just said some other software tools available if you're interested. There's a Python script described in a paper that was out last year, and the most accessible is a web app. If you go to layout.com, not now because you'll get stuck there and not pay attention to the rest of the talk, but you can basically interactively design you move your load supports, change the geometry of design domain, and see how that what the optimal structural layout is for that particular setup. And you can use it on your phone, tablet, or also obviously on your desktop. Okay, so I'm going to move now to from design to analysis and to something called discontinuity layout optimization. And how did we come across this? Well, basically, I had an interest in optimal trusses, and I worked closely with colleagues in the university who had also interest in, for example, geotechnical problems. And we observed that if you look at, for example, the figure from Michell's paper, where you've got these orthogonal lines, that was very, very similar to the layout of slipline discontinuities that you get for an ideal plastic material, Tresca material, under the action of a punch or a foundation footing loading. So what we basically realized is there's an analogy there. Turned out the analogy was known about since the 1950s by luminaries such as hemp and praga. But from our point of view, the big thing was that it meant that the numerical layout optimization tools that we developed for things like trusses could potentially be applied also to analysis problems. So what does the analogy look like? Well, if we look at each of the problems in turn, we've got the truss problems where we've got internal bar forces, equilibrium, loads, and so forth. Then they map against an entity in the slipline discontinuity problem. So instead of dealing with internal bar forces in the truss problem, we're dealing with slip line displacements in the discontinuity problem, and so forth. And what it comes out as is that you can couch your analysis problem entirely in terms of discontinuities rather than in terms of elements, which traditionally has been a much more common way of modeling a problem in the past. And basically, we trying to find the layout of these discontinuities using optimization, hence the term discontinuity layout optimization. And we published our first work in this area back in 2007. How does it work? Well, it's the same as for a truss basically, but instead of dealing with truss bars, we're dealing with slipline discontinuities in this case. And instead of identifying the optimal, so the minimum volume truss, we're basically identifying the minimum energy configuration of slipline discontinuities. Mathematics, I won't go into details here, but it's similarly a linear optimization problem. So we can solve this in a nice, simple, a nice computationally inexpensive way. The most interesting constraint is the nodal compatibility constraint. This maps to the equilibrium constraint in the truss problem. So if you imagine that these 1, 2, 3, 4, 5 lines in the left-hand side were truss bars, then what you're trying to do at the node is enforce equilibrium in the x direction and the y direction of the forces. What we're dealing with in this case, however, is potential slipline displacements. And the way to visualize that is if you're sitting, for example, just to the left of the node, and you go all the way around the outside of that node and end up back where you started from, then you need to resolve the displacements, the slipline displacements in the x direction and the y direction, so that each of those sums is equal to 0. And that basically is the key to DLO. In terms of the method in action, this is a very, very simple example. It's a footing or a panicle punch problem, and we can get to within 1% of the exact solution in about a second. Or we could 10 years ago. Computer power has increased a little bit since then, so probably a fraction of a second. A nice thing about the method is things like the singularity that you see near the edge of the footing that potentially can be problematic for finite element-based methods, where you might need to remesh, for example. You can identify that with this method without difficulty. That's a nice feature of the method. And then obviously we can move to more complex problems. These are clearly geotechnical problems. So because it's a general numerical method, you can have arbitrary geometries, and you can clearly have some fun with it. The working platform stability is a little bit tongue-in-cheek in actually showing the superstructure of the plant in this case. However, one of the most popular use case for the software is actually contractors wishing to quickly answer what if questions. Can I drive my piling rig to the top of this slope? And with traditional techniques, that has sometimes been a laborious process. And some more examples you can see here. The other thing we can do is look at different types of problems. So, for example, we've got now on screen a reinforced concrete slab analysis problem where we got 3 square slabs with different support and loading configurations, and basically we can identify the critical failure mechanism or yield line pattern, as it would be called in this case, without difficulty. And that's something that's really useful, because the traditional yield line method had fallen out of favor a bit because A, manual calculations are becoming less popular, but B, there was a real concern that if you missed the critical yield line pattern, then you would end up with an unsafe prediction of the strength, and hence you would potentially run into a safety problem. So this basically systematically automates the yield line method for slabs. And it's got a more realistic example. This is a floor plate of a building in London. This is actually one that was designed originally using the yield line method, but they had to manually explore lots and lots of different patterns, whereas with this method we can very quickly identify the critical one. And you can see the mechanism shown on the right, animated. And we actually published details of this in a paper 2-3 years ago in the ASCE Journal of Structural Engineering, which actually has this example as one of the case study problems. What are we doing now? Current work in the area of DLO. We're currently using it to analyze masonry arch bridges as part of a new project. We're looking to extend the method into effectively 2.5D, so looking at shell formulation. So we can model 3D modes of response that you get, for example, if your bridge is a skew span as opposed to a square span, or simply to take account of the different modes of response we have when we have loading, so patch or point loading, for example. And the shell formulation we're hoping will be computationally efficient, so we could hopefully be able to get rapid solutions. We had developed a 3-dimensional formulation some years ago, but unfortunately it proved quite computationally expensive, so unfortunately not immediately useful for practitioners wishing to get quick solutions. And as with the design software, there are tools available to play with if you're interested. These are from Limit State, which is a University of Sheffield spin-out company, and software is free for academic use if you're working at university. So that could be teaching or research. And I think that's sort of a quick tour of recent work in the field of layout optimization. My conclusions, and yeah, I'm biased, is that it's a powerful tool for use in both analysis and design. You can quickly get solutions, whether it be for design or for analysis, which can be, in the case of design, really insightful, can help inform what the structure should be in terms of material efficiency, which is increasingly important in the current scenario we find ourselves with global warming. And Similarly, for things like slabs or for geotechnical problems, it can find solutions which you would never find by hand. So in the old textbooks, you'll see rules to find, for example, yield line patterns, but very often, unfortunately, the true critical mechanisms are more complex than that, and hence have a lower predicted margin of safety. And the other thing to say is these layouts are visually clear and easy to interpret in many cases, and I would argue, but often, but not always, more easy to interpret than the equivalent finite element analysis output, for example. So I think that's pretty much all I wanted to say, other than to just acknowledge funding and some collaborators from, I guess, a project that I was referring to when I was talking on the design side. So many of the methods described were developed as part of EPSC funded build-up project, and that project involved University of Sheffield, but also Bath and Edinburgh, and also a number of industry partners, as you can see in the right hand of the slide. So that project officially finished last year, but we're still tidying up some loose ends from that project, and so there'll be more outputs coming in the next year or two. So I think that's everything that I wanted to say. So thanks very much, and if you've got any questions, then now's the time.
Thank you very much, Matthew, and I echo that. Any questions you have, you can type them into the Q&A box, or else if you want to ask a question in person, just raise your hand and I'll unmute you. So I have a couple of questions, maybe to start with before the questions come in, and the buckling, Matthew, because that's quite a departure from the sort of the rigid plasticity that you otherwise assume when doing this rigid plastic truss optimization. How exactly, you mentioned SDP and you mentioned a global buckling constraint. How exactly does that work?
Okay, so I thought I might get a question on this, so I think my next
Okay, great.
And I assure you that Christian wasn't briefed about this. So,
no,
so basically we augment the original formulations, the simple formulations, in the way that you can see on screen. So the global stability, we introduce a new semi-definite constraint. So clearly we've got the stiffness matrix and the geometric stiffness matrix, and the downside is that by default it increases the runtime hugely. However, with the adaptive member adding, we moderate that to a degree. For the local buckling in Peregrine, the tool that I mentioned, is actually two options. One is to include it in the latest version that actually hasn't been officially released. It's been released to selected people, but hasn't been finally released. We've actually got two options. One is to build in the buckling at the outset, and the other is to simply include it in the post-processing step. Now that isn't necessarily ideal, because if you have a design that's dominated by buckling, then your original layout that you identify that doesn't take that into account could be some distance away from the optimal. But in many cases, buckling isn't a major issue. For example, for tall buildings, for example, we end up having ample opportunity to connect columns to floor plates and the like, and you end up with buckling not being too much of an issue. On the other hand, a canopy roof can be heavily influenced by, for example, global stability.
Okay, great. Thanks. I think we might. There was someone who wanted to be unmuted. I will allow you to. I will unmute you now. Magdi, is that the right pronunciation?
Yes. Thank you. Okay, Professor Matthew, thank you for the great presentation. I was wondering, what about the dynamic loading on the structure, like when seismic and moving loads? Can Peregrine optimize the structure according to these types of loadings?
I mean, yes. I mean, you can do anything, but there are drawbacks. So, for example, one area we're looking at is frequency constraints. So, looking at, actually, this is not a civil engineering application; it's an aerospace application where we have if a component is near the engine, then you want to keep the natural frequency of vibration away from the engine frequency. So we're able to put in frequency constraints. That ends up also being a semi-definite programming problem, but we're able to again use member adding and again get solutions reasonably quickly, and hopefully you'll have that work published quite soon. For the, I mentioned the long span bridges. Now clearly long span bridges, gravity loading is very important, and that's what I focused on in that slide that I showed. But dynamics and dynamic interaction are crucially important, and that's an area that we're looking to do some work on in the future. But yeah, absolutely right. Often you can't simply take a simple quasi-static analysis approach.
Okay, thank you. So the second question is related to what do you think that the future research that can be done or needed to develop such to.
Sorry, I didn't quite catch. I think you just broke up.
Could you repeat it, Magdi, your question?
Yes. My second question is related to what do you think the future research that is needed to develop that idea or this tool?
So I see this tool or this sort of array of tools. In an ideal world, it would find its way into the software that engineers use on a routine basis. So whatever that may be, Revit or whatever. So that instead of actually being forced to place elements or to place elements and then parametrically vary them, you would actually have the opportunity to be able to identify automatically efficient arrangements for members. And similarly, I would like those big tools such as Revit to be able to have plugins which are less conservative. So, for example, for reinforced concrete slabs, they often they have plugins which is based on linear elastic analysis, and then you end up having reinforced concrete rebars that are very complex, and so potentially we should be able to deal with that scenario as well, using some of the techniques or sister techniques to the ones that I've described. So I guess I would, a little bit more work is needed in terms of integration, but also development to make this technology more mainstream.
There's a couple of other questions related to what you already, I think, talked about, Matthew. So displacement constraints and vibration of floor plates and these kinds of things. I mean, I guess it's things that in principle could be included, but at some cost compared to the more basic layout optimization. Is that right?
Yes. So many things we can add. It's just there's a price to pay. And one of the really nice things about the linear optimization or the convex optimization, so second order cone programming, other sort of sister mathematical programming techniques, is that they're really, really quick. So you can get these solutions very rapidly. And for design, that's really important. Analysis, it's maybe less important, but it's not unimportant. So having the ability to get solutions quickly is really useful. And so I guess I'm more interested in techniques which can be made to give solutions quickly, even if there are some compromises on accuracy. Because I think that's really where we need to be. We've got climate emergency. We need first order solutions that are pretty good and give solutions rapidly. We don't want to waste time on second order effects and very long run times, I would argue.
Sure. And semi-definite programming would belong to that group of problems that can be solved rapidly, right? I guess you're using a MOSEC or.
We do use MOSEC. I wouldn't say it's rapid. It's
okay.
It's affected the scale of the problem. It's a simple problem, but the scale of the problem expands very, very quickly, effectively. So.
And then you mentioned, Matthew, you're sort of a smoothed integer programming problem. So you really want to solve a 0-1 problem, but you mentioned some sort of heavy side, smooth heavy side.
Yeah.
So is that to be understood that you sort of in between iterations do some penalization of certain members, or how?
So effectively, what we in the first phase we minimize volume, and the second phase we actually have the volume as a constraint. So we say, find me the solution with, for example, the minimum number of joints, but with the volume not more than 5% above the benchmark. And we can, that's a could be couched as a smooth nonlinear optimization problem.
And then you do kind of an approximation of that in terms of a smooth problem, and then solve the smooth problem.
Small smooth problem, yeah. I mean, it works. I mean, it's a messy approach. Certainly compared with the mixed linear integer linear programming approach, which allows you to to rigorously enforce. For example, you say, actually, I want no more than 5 members, for example, or no more than 17 joints. The problem with the mixed integer linear programming formulation is that the run times can be large, and it can be quite unpredictable.
Sure.
The nice thing about the approximate smooth heaviside formulation is you can get solutions, pretty good solutions, really quickly. And you can see on the screen now, it's done a pretty good job of simplifying that truss just by varying the varying the threshold, basically. And that functionality is actually available in the layout function, in the layout program which I mentioned on screen. So this is yeah, it's there. So this allows you to basically play around with you know, a problem, and lots of changes we can make. But as a simplifier, we can then put that in. It doesn't always work. So it's rough and ready, but it, you know, it often does a pretty good job of what you ask it to do. But this is layout.com. This is completely free. Anybody can use it. And if you're an academic and you're worried about getting a classroom of students using it, then don't worry, because it's using Amazon AWS scalable. So effectively, if 1 million people suddenly wanted to use it, then well, we would end up with a big bill actually. But it would scale, and it will work. So it's actually a really nice tool just to get a feel for you know, what an optimal structure looks like, and what the influence of.
Yeah, so this would be a tool for architects as well as engineers, I guess, right?
Yeah, it could be, yeah.
Great. I think we'll have to end it here. I know you have another appointment here very soon, Matthew. So I'd like to say thank you again for a very interesting presentation, and thanks for your questions. And just a reminder that we will be back very soon in 2 weeks. George Koretsis from the University of Newcastle. That's a geotechnical talk. I hope to see you there. And so thank you, and see you next time.
Cheers.
Cheers.